Let us now move to the next section about calculation in PV systems. Consider a simple PV system including a PV panel and a DC load, which will be represented by a resistor. The PV panel is shown by solar radiation lambda and is connected to a resistance load R. How can we identify the output current I and output voltage V of the PV? We can develop the electrical response ohm volt as the system with the use of equation R equals to V divided by I. Based on the IV curve and PV curve of the PV and the ohm volt curve to identify all working parameters of the PV at specific values of lambda and R. For example, at a specific value of R when lambda is 200 watts per meter square, we start from the ohm volt to infer the working voltage value V. And next, we project vertically up to identify the working point A of the PV on its volt ampere curve, and thus we can infer the produced current of the PV. Similarly, when lambda is 500 watts per meter square, we can infer the working point B, and when lambda is 1000 watts per meter square, we can infer the working point C in the same procedure. Now, let us go through example 1. Given that a PV panel is connected to a rheostat, you are required to find the value of current IPV and the voltage UPV in 3 different cases with solar radiation of 250 watts per meter square, 500 watts per meter square, or 1000 watts per meter square, respectively. And the load resistance is changed between 10 ohms and 5 ohms, respectively. Now, please stop my video for 10 minutes and take this time to try to solve the problems on your own. Well, basing on the specifications provided by the PV manufacturer, we have the IV curves of the PV, like in the slide. To solve the first question, as the load is 10 ohms, from ohm volt of 250 watts per meter square, we can infer the voltage of 15 volt. Then, from this voltage value, we can find on the IV curve of 250 watts per meter square the current value of 2.5 amperes. When lambda increases from 250 watts per meter square to 1000 watts per meter square, as in question number 2, at the same load resistance of 10 ohms, we do the same procedure to find the voltage. Now is 46 volt and the current is 4.3 amperes. Similarly, for the case in question 3, we could find the voltage value of 38 volts and the current value of 7.8 amperes. This is the simplest example showing how the working voltage and current of a PV vary according to the change of solar radiation and the circuit load. However, in order to achieve the maximum output power from the PV system, according to the continuously changing solar irradiance, we need to use a controllable DC-DC converter as the maximum power point tracking, as shown in the diagram. The total of power consumed by the load is less than or equal to the power amount produced by the PV. So in this case, let us use here the boost converter. which which is necessary to magnify the output voltage, and then the achieved maximum output power will be inverted to feed the load. This boost converter switch is controlled by the control pulse with active or closing period D in the cycle T. During the period D, switch S is closed and connected solenoid L directly to PV panel. The solenoid is charged by the PV output power. During the rest period of the cycle T minus D, the switch S is open and the power stored in the solenoid, together with the available PV output power, will feed the load and partially charge the capacitor C through the diode D. In the successive cycle, during the switch closing period D, the load is fed by the power stored in the capacitor C while the solenoid is charged again. The power stored in the capacitor C is prevented from returning back to the PV due to the diode. Accordingly, we can infer the output voltage Vout, output voltage Vout of the DC-DC converter by the formula Vout equals DC-DC input voltage Vin divided by 1 minus D. Here we consider the cycle T to be 1. The output power Pout of the DC-DC converter is calculated as here. So to find the maximum power point, we need to adjust the value of D in a proper way so that if the load is constant, the output voltage Vout is always maximum according to the varying Vin. To do this, we make use of basic tracking algorithm. Let us use the P&O algorithm here. At a specific closing period D1, we gain the output power P1 at the working voltage value V1, and then at another closing period D2, which is randomly changed, we gain the output power P2 at a working voltage value V2. Take differentiation of P in terms of V, dP by dV. If this value is positive, that means delta P and delta V have the same sign. The working point is on the left side of PV curve over here. If P2 is greater than P1, we keep changing D in either increasing or decreasing trend as previously did until dP by dV reaches to 0, to the maximum point, or smaller than a preset value, and then stop right here. The reason why sometimes we cannot make it with 0 because it will take time for the calculation process, but when we set it with a small enough threshold value, then we can finish the calculation process earlier. That final width of D will help give the maximum power on load. Similarly, when the value is negative, that means delta P and delta V have different signs. The working point is on the right side of the PV curve as the yellow point right here. If P2 is greater than P1, we change D in either increasing or decreasing trend, reversely to what previously did, until dP by dV reaches to 0 or close enough to a preset value and then stop. That final width of D will help give the maximum power on load. Unfortunately, the disadvantage of P&O algorithm is that it causes the voltage on bus DC to vary. And thus, the electrical equipment used as the load in this circuit, in general, cannot work stably at its norm condition since the bus DC voltage following the MPPT rule is usually deviated from its norm voltage. As a result, it is necessary to develop another MPPT algorithm that can keep bus DC voltage constant or the load voltage constant as well. The solution is still basing on the adjustment of the pulse width D. Now, we have the output power of the whole PV system is calculated by this equation. Pout is equal to VDC squared by R load. With this Pout value, from the PV curve, we can identify two working voltage values, A1 and A2, each of which leads to a different related value of working current as shown on the IV curve. Of course, when we consider the efficiency of the PV system, we look forward to the ability to utilize the most solar radiation to increase Pout with least loss in the system circuit. So, which working point, A1 or A2, should be selected? Look at the point A2. We may find out that the voltage value is lower than that of A1, while the working current is around 8 amperes in comparison to that of around 2.1 amperes of A1. Obviously, for the same consumed power on load, the lower the working current is, the less power dissipation occurs in the system circuit. Therefore, for a higher system efficiency, the better selected working point is A1, which is always on the right-hand side of the maximum power point. To sum up, the maximum power point tracking DC-DC converter has two main functions. The first function is to track the maximum power point continuously for any changes, and the second function is to maintain the constant output voltage to supply the load. Let us consider example 2 as the following. A PV system working at the maximum power point tracking mode with a converter efficiency of 92% is feeding power to a bulb of 20 ohm resistance. Suppose that the solar incidence is 1000 watts per meter square. You are asked to identify the input and output currents and voltages of the converter. Again, I hope you could spend some time to solve the problem on your own before we further discuss about the solution. Now, with the solar incidence at 1000 watts per meter square, basing on the PV curve, we can find out the PV max is 386 watts. Projecting vertically up to the IV curve, we can infer the output voltage value is 39.1 volts, and the output PV current value is 9.87 amperes. These are also the input voltage and input current of the DC-DC converter. At the output of the DC-DC converter, Pout is Vout squared by R load. We can infer that Vout is equal to square root of Pout times R, or 92 times PPV times R, because the efficiency is 92%. The result achieved is 84.3 volts, and thus Iout is Vout by R, which is 4.2 amperes. Therefore, we can see that the most suitable bulbs to be mounted to this PV system are those with norm voltage of about 110 volts and non-current from 4 to 5 amperes. Now, please stop the lecture again for 10 minutes and try to solve the problem in example 3, in which every parameter is kept the same as in example 2, except the solar incidence is 500 watt per meter square. In this example, similar to example 2, let us consider the case when the solar incidence is reduced by half to 500 watts per meter square. Now, implementing exactly the same steps, you will find the PPV max is 194.5 watts. The input voltage and input current of the DC-DC converter are 39.1 volts and 4.97 amperes respectively. At the output of the DC-DC converter, we gain V out of 59.8 volts and I out. So, the voltage and current have been significantly changed. Thus, the use of MPPT module to supply the power to the load is not reasonable. For example, the voltage variation range is wide. Therefore, in order to utilize the most incident solar power, it is necessary to store the redundant solar power into batteries, or we must force the system to work in the voltage stabilization mode rather than the maximum power mode only. Only with this way, we can protect the electrical load or select the suitable ones for our PV systems. Example 4 shows you the same system except that the DC-DC converter is set to work in voltage stabilization mode to keep the output voltage constant at 48 volts to feed the 20 ohm bulb, no matter if the solar incidence is 1000 watt per meter square or 500 watts per meter square. Since the output voltage V out is 48 volts, the current I out on the load is V out by R, which is 2.4 amperes. And thus, P out of the DC-DC converter is V out times I out and equals 115 watts. Meanwhile, the expected power P in of the DC-DC converter, which is also the power PV produced by the PV, and because the converter efficiency is 92%, P in equals to 115 watts by 0.92, which is 125 watts. For this expected P in, we may see there could be two working points for each specific solar irradiance. As already explained before, we will choose the working point on the right-hand side of the maximum power point for lower losses. In this case, when solar irradiance is 1000 watt per meter square, this working point has voltage of around 48 volts and current of about 1.4 amperes. Similarly, for other values of solar irradiance, for example 750 watts per meter square or 500 watts per meter square, we still select right-hand side points and do the same to identify the working voltage and current values. The redundant electricity produced by the PV should be stored in battery to avoid wasting and also to prepare for the moments that solar irradiance is too low or unavailable, for instance, at night time. When solar irradiance is reduced to 250 watt per meter square, the maximum electrical power produced by PV, which is P in max or PV max, is smaller than the required power, 125 watts. Of course, at this moment, the PV system must automatically switch from the voltage stabilization mode to the maximum power point tracking mode and work at the maximum power point to feed the most electricity that it can produce to the load, although still not enough. In this situation, to maintain the output voltage at 48 volts, we have two solutions. The first one is to reduce the load, and the second one is to make supplement for the shortage power by supporting system, such as battery or local provider generator or grid line. For the analysis in this example, we can see that the use of battery is a must in PV systems in order to utilize the most power from the sun, or else the redundant amount of power of electricity will be wasted away. On the other hand, the battery is sometimes charged and sometimes discharged to feed the load. Thus, it requires a bi-directional switching system.